So there are three types of fancy factoring we did with the trigonometric functions. So we're going to try and apply those to all the other ones again. The first one, the difference of squares, was really handy for trig because you could end up with a sine minus a cos, which then you might be able to turn into tan. With the other functions, it's not quite as useful, but it can be done. So you would start with an example like e to the x minus 1 over e to the x. So that doesn't look like difference of squares, except you can write this e to the x here as e to the negative x. And you could turn this into something squared by making the exponent over 2, like so. And so once you have it in that format, you can see that it's an e to the x over 2 squared, subtract an e to the negative x over 2 squared. This is what our difference of squares normally looks like. So in order to execute the difference of squares factoring for that, you need your two brackets. You write the first thing. You write the second thing. Then you repeat. And to finish, one of these brackets is the positive version, one is the negative version, so that this expression can be factored that way by difference of squares, if you have a reason to do it. One that's similar, that doesn't look like it can be factored, but it can be, something like x minus 5. And that doesn't feel like a difference of squares unless I remember that x is the same as the square root of x squared, and 5 is the same as the square root of 5 squared. So once you make these transformations using the different different function notation, you can set it up as a difference of squares. So two brackets, root x and root 5, root x and root 5. One is positive, one is negative. So it does work if you have some sort of reason to do so. The other ones are a little better for actually solving equations, so I'm going to erase this and we'll try one of those. Alright, so I have a thing here plus 3 of a thing and minus 4, right? So there is no e to the x, there's an e to the x, and this, you have to remind yourself, is really an e to the x squared, using the different notation. So what I have there then is just a trinomial. So I'm trying to figure out what two numbers add to positive 3 and multiply to negative 4. So if I split that up into two brackets, the numbers that multiply to negative 4 and add to 3 would be plus 4 and negative 1. That's going to work. Now the only thing that's different about this trinomial factoring from what you would normally do is normally there'd be an x here and an x here. But x is not the thing that's in that equation. The variable in there is this exponential. So this trinomial with e to the x as its sort of functional bit factors like so. Now I have a thing times a thing equaling 0, so that means I can set up my cases. Case 1, case 2, and so I have e to the x plus 4 equals 0, or e to the x minus 1 equals 0. So to solve each case, kick the 4 over, e to the x is negative 4. You break an exponential by using a same base logarithm. So x would be ln base or log base e, which is ln of negative 4. And of course, you can't log a negative, so this fails. This case, kick the 1 over, ln both sides, and the ln of 1 is 0. So there's my only solution. So I just used trinomial factoring to split it into two brackets. And once I had the two brackets, set them up as cases, just like I did for the trig functions, and then solve for the cases, or the x values that work. So another trinomial using e to the x as the variable. This one, I try to think about numbers that would multiply to -3 and add to +1. And I'm not going to think about it too hard, because I don't think there are any. You can get 3 by doing -1 times 3 and 1 times 3, and that's it. -3. This would give me +2 in the center, and this would give me -2 in the center. None of those are what I'm after. So I'm going to need a tool in order to solve this trinomial equaling 0 when it doesn't factor tidally. Well, fortunately, you have one, right? You have the quadratic formula. So we're going to use that on this thing. Quadratic formula, exclamation point. So quadratic formula is -b plus or minus square root of b squared minus 4ac all over 2a. Now normally that would be equal to x, because our quadratics usually had x squared plus 1x minus 3. But this is not a normal quadratic. This is a quadratic that uses the exponential as its base. So instead of an x here, I write e to the x. Other than that, it's exactly the same. So e to the x would be, the b value is 1, so -1, plus or minus b squared is 1, minus 4 times the a value, which is 1, times the c value, which is -3, all over 2 times the a value. So e to the x would be equal to -1 plus or minus the square root of -4 times -3 is 12. 12 plus 1 is 13 over 2. So that's created two cases for us. Case 1, case 2. Oop, 2, not question mark. Case 1 would be e to the x equals -1 plus root 13 over 2. Case 2 would be e to the x equals -1 subtract square root 13 over 2. Now to finish these, I'm going to have to actually solve for x. So under case 1, I'm going to break this exponential by using ln. So I'd have ln of, I'm going to switch these just for convenience, root 13 minus 1 cut in half. On this side, I have to do the same thing. It's ln -1 subtract root 13 over 2. Now, -1 subtract 13, that's going to be a negative. And you can't ln a negative, so I already know that this one doesn't work. But I could try this one. So if I get out the calculator, let's see, x is ln root 13. Root 13 is about 3.6. Subtract 1 is 2.6 divided by 2 gives me 1.303 approximately. And if I ln that, ln of my answer, I get 0.264 approximately. So I was able to use the quadratic formula on this thing with exponentials in it. It worked out just fine. Once I got my cases from quadratic formula, just like you did with parabolas, I was left with the extra step of having to actually solve this functional piece. So the same idea, but I'll toss a logarithm in there instead of the exponential. First thing I'm going to try is factoring it to see if I can come up with two numbers that multiply to negative 10 and add to negative 3. And I think that will work for negative 5 and plus 2. And because ln x is the thing here, right, the thing that's there and then there again squared, this is going to be ln x subtract 5 and ln x subtract 2 equaling 0. So I've created two cases there, case 1 and case 2. Because anytime you have a thing multiplied by a thing equaling 0, you can separate them out. So case 1 would be ln x minus 5 equals 0. Case 2 would be ln x subtract 2. Plus 2 equals 0. To solve this case, I kick the 5 to the other side. You break logarithms by raising to an exponent of the same base. So I'd have x is e to the 5. And over here, ln x equals negative 2. So x equals e to the negative 2. Whatever those numbers are if you put them into the calculator. So here we have another trinomial with a ln x instead of the e to the x like we did before. It's possible that that factors. I have a number in front which says I might be able to pull this off if I did decomposition type factoring. If you're good at that, then you should do that. If not, you can leap directly into the quadratic formula, which is what I'm going to do here. So my quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. And because ln x is the thing that's driving this, it'll be ln x equals that instead of just x. So if I fill all these numbers in, ln of x would be negative 3, which is just 3. Negative 3 squared is 9 minus 4 times an a value of 2 and a c value of 1 all over 2 times the a value, which is 2. So ln of x would be 3 plus or minus the square root of 2 times 4 is 8 times 1 is 8, 9 minus 8 is 1, 2 times 2 is 4. So ln of x would be 3 plus 1. Be 4 divided by 4 is 1, 4. 3 subtract 1 would be 2. 2 divided by 4 is 1/2. So either ln x equals 1 or ln x equals 1/2. I have my two cases. So I just have to finish them off. I break a ln by raising to an exponent of the same base, e to the 1. So x is just e. And over here, x would be e to the 1/2. So same thing, I just used quadratic formula with a ln inside of the argument and got my two solutions that way. So this one, when the radical is involved, it doesn't look like a trinomial at all, right? I don't have something squared out in the front. Unless you remember that root x squared, those two things undo each other and will leave you with just x. So if I make that replacement here, that this is root x squared minus 5 root x minus 6 equals 0, suddenly I have something that works for simple trinomial factoring. So I just need two numbers that multiply to negative 6 and add to negative 5. And the numbers that are going to work for that are negative 6 and plus 1. And since the square root x is the business part of this function, in it goes, which has generated my two cases to solve. So case 1, case 2, either root x plus 1 equals 0 or root x minus 6 equals 0. So to solve this case, kick the 1 to the other side. Square both sides. 1 negative 1 squared is 1. This one, kick the 6 over. Square both sides. X would be 36. All right. Well, since the radical is involved, you have to actually test it to see if these solutions work. So using x in my original function, 1 minus 5 times the square root of 1 minus 6. Well, that is 1 minus 5 minus 6, which is negative 10, which is not 0. Grouchy face. So this solution here, it didn't work because that negative was eliminated in the process of squaring. So if I try the other solution, using 36 as my x, 36 minus 5 times the square root of 36 minus 6 would be 36 minus 5 times 6 minus 6 should be 36 minus 30 minus 6, which is 0. That one worked. So this solution is valid for that particular equation. And all I had to do to make this work was to remember to replace an x with a root x squared, and then I was able to get away with some simple trinomial factoring. So the last example here is one I'm going to use quadratic formula on. The way I can tell that is it has a number out in front. You could attempt to do factoring by decomposition, and that might work, it might not. I'm just going to launch into quadratic formula because I know it's going to work for me. The only thing I have to remember to spot this is that this thing here is really root x squared, which is what's going to let me get away with my quadratic formula. So in this particular example, quadratic formula is negative b plus or minus square root of e squared minus 4ac over 2a. And the busy part of this function is a root x. So filling in the coefficients, root x would be negative 2 would be negative 2 plus or minus. 2 squared is 4 minus 4 times the a value of 5 and a c value of negative 3. All divided by twice the a value, which was 5. Gives me negative 2 plus or minus the square root of 3 times 4 is 12. 12 times 5 is 60. 60 and 4 is 64 over 10. So root x is negative 2 plus or minus 8 over 10. So case 1, root x would be minus 2 plus 8 is 6 over 10, which reduces to 3/5. Or case 2, root x would be negative 2 subtract 8, which is negative 10 divided by 10, which is negative 1. To finish this case, I need to square. That would be 9/25, or x equals 1. And one more time, you have to go through and you have to test these because it came from a radical. So 5, I'll do this first one. 5 times 9/25 plus 2 times the square root of 9/25 minus 3. Well, that would be 9/5 plus 2 times 3/5 minus 3. That would be 9/5 plus 6/5 minus 15/5 is 0. So that one worked out. Testing the other one, 5 times 1 plus 2 times the square root of 1 subtract 3 gives me 5 plus 2 subtract 3, which is 4, which is not 0. Grouchy face. So this particular solution didn't work because that negative was eliminated in our algebra process. So you should be good to try some trinomial factoring or quadratic formula on the questions in the problem set.